Right now, as you read this, an ancient whisper from the universe's infancy washes over you. It's a faint, uniform hum of microwave radiation, the oldest light in existence, a cosmic baby picture taken just 380,000 years after the Big Bang. This light, the cosmic microwave background, should be a smooth, perfect echo of creation with only tiny ripples that blossomed into every star and galaxy we see. But zoom in, and a colossal, impossible bruise screams into existence, spanning 1 billion light years across, a region of space so vast it could swallow 1,000 Milky Ways. This is the cold spot, a wound on the face of the early universe, impossibly colder and emptier than anything our cosmos should ever allow. What if this isn't just a statistical fluke, a cosmic accident? What if this immense, chilling void is actually the smoking gun of an event so cataclysmic, so mind-shattering, it redefines reality itself? The violent impact of our universe slamming into another? You just felt it, that ancient whisper, that faint hum from the universe's ultimate baby picture, the cosmic microwave background, or CMB. It's not just light, it's the fossilized afterglow of the Big Bang itself, a cosmic snapshot taken when the universe was barely a toddler, just 380,000 years old. Before stars ignited, before galaxies spun into being, the entire cosmos was a dense, searing hot fog of plasma. Then, it cooled just enough for light to break free, flooding space with this primordial glow. This light should be almost perfectly uniform, a smooth, warm blanket stretched across the heavens. And indeed, it largely is. Its incredible uniformity is a cosmic triumph, proving our universe burst forth from a state of near-perfect balance. But within that perfect uniformity, subtle, crucial ripples did exist. Think of a perfectly still pond. Then imagine the faintest breath of wind disturbing its surface, creating tiny, almost imperceptible waves. These were quantum fluctuations, microscopic wobbles in the universe's earliest moments, amplified by inflation into seeds. Gravity then latched onto these tiny seeds, pulling matter together over billions of years, slowly sculpting the vast cosmic tapestry we observe today. The dazzling galaxies, the colossal clusters, the intricate web of dark matter holding it all together. The CMB's temperature map shows us these initial variations. Some regions infinitesimally hotter, some infinitesimally colder. The blueprints for every structure in existence. It's a cosmic fingerprint, revealing the precise conditions that allowed stars, planets, and ultimately, us, to emerge. Yet staring back from this ancient portrait is something that defies every rule, every expectation, every model we have built. A colossal, chilling void. The cold spot, it's a vast spherical region of the CMB, stretching a staggering 1 billion light years across, where the temperature is significantly, impossibly, colder than its surroundings. We're not talking about a subtle dip. This is a gaping maw of cosmic cold, a negative temperature anomaly that stands out like a black eye on the universe's baby face. Imagine baking a perfect cake, uniform in every way, then finding one section of it is frozen solid, while the rest is perfectly warm. This isn't just a minor baking error, it's a profound, chilling mystery. This isn't just a region with fewer galaxies, it's a region that has been fundamentally, consistently colder and emptier since the dawn of time. Standard cosmological models, our most trusted guides to the universe's evolution, struggled to explain its very existence. The statistical probability of such an extreme anomaly forming by random chance is vanishingly small, less than 1 in 10 million. That's like flipping a coin and having it land on heads 23 times in a row. The universe, by all accounts, should not have been able to create such a colossal, persistent scar through normal random fluctuations. The cold spot screams that something fundamental is missing from our understanding, a glaring cosmic glitch that threatens to unravel the entire story of our universe. Our universe, as we understand it, largely dances to the tune of the Lambda CDM model. This isn't just a theory, it's our cosmic blueprint, our grand unified story of creation, built on the bedrock of dark matter, dark energy, and the Big Bang. It paints a picture of a cosmos that started incredibly hot and dense, then expanded, cooled, and crucially, developed structure from those tiny, predictable temperature fluctuations we saw in the CMB. Lambda CDM predicts a universe that, on the largest scales, should be remarkably uniform, with any variations smoothing out over time, leaving only a statistically predictable distribution of galaxies and voids. It's a model that has triumphed, explaining everything from the abundance of light elements to the accelerating expansion of space. But the cold spot, it punches a gaping hole in that perfect blueprint. This isn't just a minor statistical blip. It's a cosmic middle finger to our most cherished model. Imagine building a magnificent, perfectly symmetrical skyscraper, only to find one entire section of its foundation is inexplicably, impossibly missing. The statistical nightmare it presents is staggering. The chance of a region this cold, this vast, appearing purely by random chance in a Lambda CDM universe is less than 1 in 10 million. That's not just improbable, that's beyond improbable. That's the universe whispering, or rather screaming, that something is fundamentally off. We've tried to explain it away. Could it be a supervoid, an enormous empty bubble of space where galaxies simply never formed? We know supervoids exist. Gravity naturally pulls matter out of less dense regions, creating these vast cosmic deserts. And indeed, the cold spot is associated with a supervoid. But here's where the glitch gets truly profound. Even the most extreme supervoids, packed with whatever dark matter should still reside within them, simply cannot explain the temperature drop we observe. The integrated Sachs-Wolf effect, where CMB photons lose energy as they climb out of the shallower gravitational wells of voids, can account for some of the coldness, but not nearly enough. The cold spot is still far, far colder than any known supervoid should make it. This defies the very principle of cosmic uniformity, the idea that the universe should look roughly the same in every direction on large scales. It's a stubborn, defiant anomaly, a cosmic scar that refuses to heal, refusing to conform to the elegant mathematical perfection we've constructed. It's as if the universe has a hidden, rogue element, a secret mechanism that occasionally throws a wrench into the cosmic machinery. This persistent anomaly forces us to ask, is our cosmic blueprint flawed? Or is the cold spot a signpost, a profound, chilling clue pointing to physics beyond our current understanding? If the very idea of a universe with such a fundamental, unexplained glitch, a scar that defies all logic, fills you with the same awe and existential dread it fills us, then smash that like button. And for more journeys into the most mind-bending secrets the cosmos holds, subscribe to the channel. We're just getting started. So, if the cold spot isn't just a statistical fluke, and no known cosmic structure can fully explain its impossible chill, then what is it? This is where science truly becomes a detective story, where we chase the most audacious, terrifying, and utterly mind-blowing explanations. And the boldest theory, the one that makes your very atoms tingle, is this: the cold spot is a cosmic bruise, a literal scar left on our universe from a violent, primordial collision with another universe. Picture the cosmos not as a single, isolated bubble, but as a vast, frothing ocean of realities. This is the multiverse hypothesis, and it's not science fiction anymore. It's a serious, active area of theoretical physics. Imagine countless bubble universes, each potentially governed by its own unique laws of physics, floating and drifting through a higher dimensional space. Our universe is just one of these bubbles, expanding and evolving. Now, what happens when two bubbles in that cosmic foam drift too close? They don't just gently brush, they can collide. A violent, unimaginable impact on scales that dwarf our comprehension. Such a collision wouldn't be a neat, clean event. It would be a cataclysmic shockwave ripping through the fabric of nascent realities. When our universe, still in its infancy, perhaps just a fraction of a second old, slammed into another, it wouldn't have shattered like glass. Instead, the force of the impact would have left a thermal imprint, a kind of cosmic contusion. Think of it like a giant, super hot billiard ball striking another. The point of impact would transfer energy, creating a disturbance. In the early universe, this disturbance would manifest as a cold spot. Why cold? Because the collision might have momentarily pushed matter away or altered the very expansion rate in that localized region, causing it to cool faster than its surroundings. It's a cosmic shiner, a black eye from a fight we didn't even know we were in. This isn't just a random guess. It's rooted in specific theoretical frameworks, particularly those emerging from inflationary cosmology. Inflation, the period of super rapid expansion in the early universe, naturally leads to the idea of a multiverse. If inflation never truly stops everywhere, but rather ends in patches, each patch can become a new bubble universe. And if these bubbles are constantly forming, they're bound to bump into each other. The cold spot in this scenario becomes direct, tangible evidence of this cosmic bumper car ride. The implications are staggering. If the cold spot is indeed a bruise from another universe, it means we are not alone. Our reality is not singular, but merely one thread in an infinite tapestry of existence. It means the very concept of our universe is limited, a mere speck in a boundless, multi-dimensional expanse. This isn't just about finding a cold patch in the sky. It's about tearing down the walls of our cosmic perception, about glimpsing a reality so much vaster, so much more complex, that it redefines our very place within it. It transforms a puzzling anomaly into a portal, a window into a hidden, infinite cosmos. If the cold spot truly is a cosmic bruise, then the next question screams from the darkness: where are the forensic clues? How do we find the definitive evidence for a cosmic car crash? Scientists are not just theorizing, they're hunting for subtle, tantalizing echoes of this unimaginable impact, looking for the telltale signs that scream another universe was here. One of the most crucial pieces of evidence lies in the shape and texture of the cold spot itself. If it were merely a gigantic supervoid, its temperature profile should be relatively smooth and spherical, but a collision, that could leave a more complex, irregular imprint. Imagine two soap bubbles merging. The boundary where they touch isn't always perfectly round. Scientists are using advanced statistical techniques to analyze the cold spot's exact contours, looking for subtle anisotropies, peculiar elongations, or even tiny hotspots within the cold region that could betray the angle and force of a collision. The precise way the temperature varies across the cold spot could be a direct signature of the impact's geometry, a cosmic fingerprint of an interuniversal encounter. Then there's the hunt for nearby anomalies. If our universe collided with another, the impact wouldn't just leave a thermal scar. It might also have perturbed the distribution of matter in that region. We're talking about unusual patterns in galaxy distribution around the cold spot. Do galaxies cluster differently near its edges? Are there unexpected voids or superclusters that can't be explained by normal gravitational evolution? These could be the ripple effects of the collision, like debris scattered from a cosmic impact zone. Gravitational lensing, the bending of light by massive objects, offers another powerful tool. If the impact disturbed the dark matter distribution, it would subtly distort the light from background galaxies passing through the cold spot's vicinity. Detecting these distortions would provide direct evidence of unusual matter arrangements, a cosmic X-ray revealing the hidden damage. But the real holy grail, the ultimate smoking gun, would be the detection of Earth's non-Gaussianity. This is where it gets truly mind-bending. Standard Big Bang cosmology, as amplified by inflation, predicts that the initial fluctuations in the CMB should be Gaussian, meaning they follow a predictable bell curve distribution. Think of it like a perfectly random scattering of dots on a page. But a collision with another universe, especially one with different physical properties, would introduce non-Gaussian features, irregularities, lumps, or patterns that simply shouldn't be there by chance. It's like finding a perfectly random scattering of dots, but then noticing a distinct, non-random smiley face hidden within them. Detecting these non-Gaussian signatures in the cold spot's temperature variations would be a monumental discovery, a direct challenge to the fundamental assumptions of our standard cosmological model. The challenge is immense. These are incredibly subtle signals, buried beneath layers of cosmic noise. We need exquisitely sensitive instruments, like the Planck satellite that first mapped the cold spot in detail, and future observatories with even greater precision. We need to filter out foreground emissions from our own galaxy, account for every known cosmic phenomenon, and then, with surgical precision, extract these faint, alien whispers from the universe's oldest light. But if even a single piece of this forensic evidence holds up, if we find a statistically significant non-Gaussian signature, or a peculiar galaxy distribution that screams collision, it won't just confirm a theory. It will shatter our cosmic solitude, proving beyond a shadow of a doubt that our universe is not alone and that our reality is just one fragile, beautiful bubble in an infinite, unimaginable sea. Our journey through the cold spot has pulled back the veil on a universe far more awe-inspiring and terrifying than we dared to imagine. This billion light-year bruise on the face of the cosmic microwave background is more than just an anomaly. It's a defiant whisper from the edge of reality, a potential testament to a collision that occurred before stars even began to flicker. It forces us to confront the most profound question: are we truly alone in the cosmos? Or is our universe merely one bubble in an infinite frothing sea of realities? If the cold spot is indeed the imprint of another universe, it shatters our cosmic solitude. The very fabric of existence expands beyond our singular bubble, revealing a multiverse that dwarfs even our grandest imaginings. It means the laws of physics that govern our reality might simply be our laws, one set among countless others. This isn't just a scientific discovery, it's an existential earthquake, a redefinition of what universe even means. Yet this knowledge isn't about diminishing our place. It's about amplifying the miracle of our existence. In a cosmos potentially teeming with countless realities, the fact that this universe, with these laws, allowed for the emergence of consciousness, for us to even ponder such mysteries, becomes an even more precious, improbable triumph. The cold spot, in its chilling silence, reminds us that the universe is not a closed book, but an endless saga of discovery. It stands as a cosmic challenge, a monument to the questions that still rage at the frontiers of human understanding. What truly is dark energy? How did the universe begin? And what other realities might be drifting, unseen, just beyond the edges of our own? The cold spot calls to us, a silent siren song from the depths of cosmic emptiness, reminding us that even in the absence of light, there is everything left to discover, everything left to understand about the mind-bending nature of existence itself. Tell me what you liked or disliked about this video. What do you think could be changed to make it better? I read every comment and will respond to every suggestion.